Solubility product constant, also known as KSP. So for our dissociation equations, we're going to stick to writing the solid on the left-hand side of the equation and putting the ions on the right. So we're dissociating a solid into its ions. As they dissolve, they become aqueous. And we're going to stick to writing the solid on the left, the ions on the right, because then when we write our equilibrium expression, we don't end up with a 1 over something. We can stick to not having fractions. So recall that equilibrium expression for any dissociation will incorporate the solid concentration, which does not change, into the already constant K value. And so we would not have the solid written on the denominator here as we wrote it on the left. It would end up on the denominator as a reactant. And so our KSB expression for the dissociation of any ionic substance is just going to be the concentration of the ions raised to their coefficients in their balanced dissociation equation. And so if there's 2 chloride ions being formed, we need to make sure we put a exponent 2 after that chloride ion. Instead of just calling it K, we're going to specify that it is the solubility product constant, and so we write K with a subscript SP after it. So given the amount concentration of a solute dissolved, so how soluble it is, its solubility, we can use the solubility product constant to calculate out the solubility product. Essentially we have our KSP expression, gives us our ions, let's say it forms ion A and ion B. So either we can use KSB to find the concentration of the ions, or we can use the concentration of the ions to find the KSB. So let's try it here, where we are looking at determining the KSB of silver bromide, given that it has a molar solubility of 5.71 times 10 to the negative 7 moles per liter, so not particularly soluble. But the first thing that we'd want to do is to set up the dissociation equation for the dissolving of the silver bromide. So again, put the solid on the left. We're going to set it up as an equilibrium expression, so it'll dissolve to the point of saturation. We have a silver ion and 1 bromide ion forming, so a 1:1:1 ratio. We can write the KSB expression for this, and again, it's not that we see them here because they're 1s, but there are exponents of 1s for both the silver and the bromide because there are coefficients of 1 in the equilibrium expression for its dissociation. It's a 1:1:1 ratio, so when we say that 5.71 moles per liter have dissolved, that is the amount of ions that have been put into solution. It is also, because it's a 1:1 ratio, the amount of bromide ions that have ended up in solution. So it's important to realize what the molar solubility means, and it essentially gives you the concentration of their ions as long as you factor in the molar ratio. So the amount of silver bromide that has dissolved, not its concentration as a solid, but the amount that actually did dissolve to make these silver ions and these bromide ions, is the 5.71 times 10 to the negative 7. So we end up with 5.71 times 10 to the negative 7 silver ions, 5.1 times 10 to the negative 7, 5.71 times 10 to the negative 7 moles per liter of bromide ions as well. Plug those into your equilibrium expression. And again, it's a 1:1 ratio. If it wasn't, we'd have to factor that in at this point. And we'd have to factor in these exponents are also 1 and 1. So we have to be aware of that. And we end up with a KSB of 3.26 times 10 to the negative 13. All right, so let's try one where we're given the KSB and we look for the molar solubility. So this is lead 2 iodide, and it has a very low KSB, not very soluble. So start with the dissociation equation. Again, solid on the left, ions on the right. Write your equilibrium expression. Don't forget to factor in the 2, becomes the exponent there. And we know that the KSP is 9.8 times 10 to the negative 9. We don't know how much currently the lead ions are being put into solution, but we do know that it's going to be something, and the amount of iodide ions, because for every lead ion that you make 2 iodide ions. And so we would end up with 2 times the concentration of lead going in as our concentration for iodine, and the coefficient is also there as a 2. So those are 2 separate things we got to be aware of, is that we are doubling the concentration because that's where the iodide is coming from. There's 2 ions coming from the lead iodide, 2 iodide ions, and because there's a coefficient of 2, there's an exponent of 2, so we're going to factor that in as well. And that's just a matter of solving for x. And you end up with 1.3 times 10 to the negative 3. And this is the x value, which is the concentration of lead, or half the concentration of iodine. So if they're asking for what is the molar solubility, how much of this lead iodide went into solution, we just found that our x value being 1.3 times 10 to the negative 3. So that must be the amount, because for every lead ion that you get is because you got at that amount of lead iodide or lead 2 iodide dissolving. So this is the amount of lead that was in solution. Therefore, it must also be the amount of lead 2 iodide that did dissolve. It is its molar solubility. So we can say the molar solubility of lead iodide, the amount that dissolved, is 1.3 times 10 to the negative 3 moles per liter.